People often have this idea that lHpital's rule is really great. I want to tell you why you shouldn't fall in love with lHpital's rule. For one thing, lHpital's rule often leads to circular reasoning. Let's go to the blackboard and take a look. For example, here's a problem that you might be tempted to use lHpital on. You want to know the limit as x approaches 0 of sine x over x. Now, what do you have to check? Well, let's take a look at the limit of the numerator by itself. The limit of sine x as x approaches 0, sine's continuous, so that limit is just sine of 0, which is 0. Numerator's limit is 0. Limit of the denominator, the limit of x as x approaches 0 is 0. So yeah, this is a 0 over 0 indeterminate form. So we try using lHpital. lHpital tells us that this limit is equal to the limit as x approaches 0 of the derivative of the numerator, which is cosine x, over the derivative of the denominator, which is 1. Now this limit is quite a bit easier to do, right? This is really just the limit of cosine x as x approaches 0. Cosine's continuous, so this is just the value of cosine at 0, which is 1. And yeah, I mean, the limit of sine x over x as x approaches 0, it is in fact 1. This looks good, right? The question, though, is how did you know that the derivative of sine x was cosine x? You needed to know that in order to apply lHpital. How did you know the derivative of sine x was cosine x? Well, let's think back. Right, so how did I know that the derivative of sine x was cosine x? Well, taking a derivative is the same thing as a limit of a difference quotient. So to calculate, say, the derivative of sine at 0, I take a limit like this. The limit as h goes to 0 of sine 0 plus h minus sine 0 over h. Sine of 0 is just 0. So calculating this limit, which is calculating the derivative of sine at 0, it's really the same as calculating the limit as h goes to 0. Sine 0 plus h, that's just sine h, minus 0 over h. Now, what just happened? I wanted to calculate the derivative of sine at 0. And to calculate the derivative of sine at 0 is really the same as calculating the limit as h goes to 0 of sine h over h. It's the definition of derivative. And I was going to use this to evaluate the limit of sine x over x using lHpital. Right? lHpital doesn't just reduce a limit problem down to another limit problem. It reduces a limit problem down to a limit problem and two derivative problems. Right? To do lHpital, you have to be able to differentiate the numerator and denominator. So if you're going to use lHpital to evaluate sine x over x as x goes to 0, you're going to have to differentiate sine x. But then to differentiate sine x at 0, which is what you're trying to do to use lHpital, you have to be able to evaluate this limit, the limit of sine h over h. You have to be able to do the limit you're trying to do already. It's just circular reasoning. So what just happened? I was trying to calculate the limit of sine x over x as x approaches 0. I used lHpital. lHpital told me to differentiate sine x. But then to differentiate sine x, I would have needed to be able to evaluate the limit of sine h over h as h goes to 0, the exact problem I'm trying to solve. It's an example of circular reasoning. There's other things that can go wrong with lHpital. One of the conditions in lHpital is that the limit of the ratio of the derivatives has to exist. And let's see an example where that fails to happen. Here's an example. Let's take a look at the limit of x plus sine x over x as x approaches infinity. Try to use lHpital. So I want to look at the limit of the numerator by itself. The limit of x plus sine x as x approaches infinity is infinity. The limit of the denominator by itself, the limit of x as x approaches infinity, also infinity. This is an infinity over infinity indeterminate form. That seems good. Now lHpital tells me that to calculate this, I should look at the limit as x approaches infinity, the derivative of the numerator, which is 1 plus cosine x, over the derivative of the denominator, which is 1. Now, what's the limit of 1 plus cosine x as x approaches infinity? Well, the limit of 1 is just 1, but what's the limit of cosine x as x approaches infinity? Right? Cosine just oscillates between minus 1 and 1. This limit doesn't exist. This limit doesn't exist. Now, does that mean that this limit doesn't exist? I wrote equals here, but remember, I'm using lHpital's rule. Right? And what does lHpital's rule actually say? It says that this limit is equal to the limit of the derivative over the derivative, provided this limit exists. And this limit doesn't exist in this case, so lHpital is silent as to the value of this limit. Let's see if we can actually compute that limit some other way. All right, so let's try to do this limit some other way. I'm going to do the limit of x plus sine x over x goes to infinity without using lHpital. This is the limit of a fraction. I could split up the fraction as a limit as x goes to infinity of x over x plus sine x over x. Now that's a limit of a sum, which is a sum of the limits provided the limits exist. So this is the limit as x goes to infinity of x over x plus the limit as x goes to infinity of sine x over x. Now what's the limit of x over x as x goes to infinity? Just 1. What's the limit of sine x over x as x goes to infinity? Well, sine x is always between minus 1 and 1. And x here is going to infinity. I can make x as big as I like. So the question is, can I make this as close to 0 as I like? Yeah, by making x large enough, a number between minus 1 and 1 over x can be made as close to 0 as I like. So this limit is 0. So the sum of the limits is 1, and that's the limit of the sum. That's the limit of x plus sine x over x. It's 1 as x goes to infinity. And this is true in spite of the fact that lHpital failed us, right? When we did lHpital in this problem, I was told to differentiate the numerator, divide by the derivative of the denominator as x goes to infinity, and that derivative didn't exist. It was oscillating between 0 and 2. And in that case, lHpital is just silent. lHpital requires that limit of the ratio of the derivatives to exist, and if it doesn't exist, lHpital doesn't say anything. This limit does exist, and then to see that requires some algebraic computation. So we managed to evaluate that limit. The limit was 1, but no thanks to lHpital. The limit of the ratio of the derivatives didn't exist. It was oscillating. We evaluated that limit by algebraic manipulation. And don't get me wrong, lHpital is awfully powerful. There's plenty of situations where you want to use lHpital, but often you can get away with just doing some algebraic manipulation. So I encourage you, when you're doing these limit problems, don't forget that you can just algebraically manipulate things. Right? There might be an easier way than bringing out lHpital. Only use lHpital if you absolutely have to use lHpital. In other words, don't fall in love with lHpital.